Good morning, everyone, and thank you for joining our expert sessions. Today, Sonny is the one that is going to give this webinar. So Sonny is an electrical engineer with a Bachelor on Engineering in 2015 from McMaster University in Canada. He has 8 years of experience in protection system and relays. Sonny has educated consultants and end users to the benefits of implementing electrical products into their designs to achieve safety for personnel and equipment. And he is focused on providing timely commercial and technical support for projects and applications, including high resistance grounding systems, low resistance grounding system, hybrid HRD systems, ground fault and arc flash protection systems, resistor-based solutions, and people protection products. So thank you, Sonny.
Hi, everyone, and thank you for coming to this expert session on system grounding techniques and the role of resistance grounding in industry standards. The focus of our presentation for today is going to revolve around, we're going to be discussing ground faults in greater detail. So what is a ground fault exactly? Well, a ground fault is an unwanted connection between the system conductors and ground. Ground faults often go unnoticed and cause havoc on plant production processes, shutting down power and damaging equipment, leading to hours or even days of lost productivity, which can cause grief to your customers since for every minute or hour or day of downtime, it causes financial issues. Ground faults can lead to safety hazards such as fire and electrical shock, and they're typically caused by loose connections, worn wire insulation, exposure to moisture, or any external natural condition, such as the environment. In some cases, along the coastal lines, you may see the impact of salt that would damage or wear down insulation faster than in normal conditions. Even in certain cases far up north, we could see the impacts of very cold weather and lack of humidity cause issues for electrical equipment. Now, according to the Industrial Power System Grounding Design Handbook, 95% of electrical failures are of the phase to ground type. So when we're utilizing a high resistance grounding system, we're essentially tackling 95% of electrical failure cases in limiting that fault current to a specific value. The remaining 5% consists of 4% being phase-to-phase faults, and the remaining 1% as three-phase faults where all three phases are shorted against each other. So let's talk about ungrounded systems first, which is not as popular in North America, but is quite popular in Europe. So for an ungrounded system, these were typically utilized in process industries where the first ground fault cannot be tolerated with respect to tripping out the system. And in that case, process industries decided to use ungrounded systems because upon the first fault in this type of system, they may continue operating even with the fault still contained in the system. So they offer a very low value of current flow for line to ground fault, and that is because of the capacitance that exists between the conductors and ground, which basically dictate how much ground fault current there will be in the system. The issue with ungrounded systems is that with respect to the three phases and ground, there is no direct system ground between the three phases and ground, and as a result, there's only a bonding network. There's no return path for any ground fault current, so it's extremely difficult to locate line to ground faults in this type of system. And in addition to that, the transient overvoltage scenario on the unfaulted phases when there is a ground fault can be up to 6 to 8 times the line to neutral voltage of the system, which is problematic because your insulation can degrade at a much faster rate, and you may eventually lead to a phase-to-phase failure, which can either knock out your system or cause severe damage. So in the IEEE standards, they refer to this transient overvoltage. These overvoltages, which can be several times normal in magnitude, result from a resonant condition being established between the inductive reactance of the system and the distributed capacitance to ground. And this magnitude can be as high as 6 or 8 times the phase voltage. Such overvoltages can puncture insulation and result in additional ground faults. So there is a bit of difficulty in trying to locate these types of faults. So when these transients occur in these ungrounded systems, we can basically have a very hard time in terms of troubleshooting this type of system, since we'd have to isolate every single breaker and figure out where the ground fault is coming from, first of all, and then second of all, if that even solves our issue, how are we going to deal with the damage done from the transients while that ground fault was still in the system? Now, 60 to 70% of the time in the North American market, the systems that we utilize are solidly grounded. And in a solidly grounded system, you would have like a delta Y transformer, where the exo point of that Y side is connected directly to ground. In this case, a solidly grounded system will eliminate the transient overvoltage by shorting out the capacitance that exists between conductors and ground. And it allows users to easily locate faults because now there's a ground return path for fault current to flow through. We can also support single phase loads, which is a big reason why solidly grounded systems are utilized quite often to power commercial residential. The only cons are that when the ground fault does occur in the system, thousands of amps can flow back through this solid connection back to the source, and that can create an arcing condition if the process is not interrupted when there's a ground fault. So when a ground fault occurs in this system, there's no process continuity because of the high values of fault current that can cause severe equipment damage. So in a sense, you're sacrificing the process continuity for additional level of safety. And in addition to that, solidly grounded systems have a tendency to be a cause for arcing faults. So here we can see in IEEE standards, we have the red book and the buff book. The danger of sustained arcing for phase to ground fault probability is high for 480 and 600 volt systems. A safety hazard exists for solidly grounded systems from the severe flash, arc burning, and blast hazard from any phase to ground fault. And on the right hand side, we can see that one disadvantage of the solidly grounded system involves the high magnitude of destructive arcing ground fault currents that can occur. So keep that in mind with respect to solidly grounded systems. Obviously, when you have a three-phase four-wire system, you have no choice but to use it. But in the case of three-phase three-wire systems, there may be a better solution. And that solution leads us into resistance grounding. For resistance grounding, what we do is we employ a resistor from the exo point to ground, where the system will still have a ground reference for fault current to flow through, but this time we're placing a resistor in series with that fault current to basically clamp that current to a specific value. So resistance grounding involves adding the impedance between the transformer, neutral, and ground. This keeps the ground fault current at a low level, preventing the buildup of sufficient energy for arcing and making the system safer to operate. It's typically utilized in low voltage and medium voltage systems to limit ground fault current. There's no arcing ground faults as with solidly grounded systems when the ground fault is of the phase to ground type. We're limiting that fault current and there's insufficient energy for the arc to restrike and therefore it extinguishes itself. And we also control the overvoltage condition in comparison to an ungrounded system because we're placing this resistor in parallel with the capacitances that exist between conductors and ground. And as long as we size this resistor according to that capacitance, we will control the transient overvoltage to a manageable number that the insulation of the cable can handle. So here are some references from the IEEE Green, Red, and Buff books. So on the left-hand side, we could see that the Green book specifies quite a few um, uh, information. So to reduce burning and melting effects in faulted electrical equipment, such as switchgear, transformer cables, and rotating machines, since we're limiting that fault current to a specific value, the effective current coming from that limitation is manageable to the switchgear, transformer, the cables, and the loads. We're also reducing mechanical stresses in the circuits and apparatus carrying fault currents. We're reducing electrical shock hazards to personnel as well from stray ground fault currents in the ground return path. And we're also reducing arc flash or flash hazard to personnel who may accidentally caused or happen to be in close proximity of the ground fault. We know that high resistance grounding helps ensure a ground fault current of known magnitude, making it possible to identify the faulted feeder with sensitive ground fault relays. And we are also able to satisfy continuous operation while this 5 amps is circulating and the system is still running, including the faulted feeder, which is causing the first fault into the system. So let's take a look at this 480 volt system that has been drawn out. That is 3-phase 3-wire. We've placed a resistance of 55.4 ohms from the neutral point to ground in an effort to limit fault current to 5 amps in this scenario. At the moment, our system is currently in no fault condition, and you can see that our phase to ground voltages are still intact at 277 volts. I've drawn out the capacitance here to showcase that the capacitance that leads to ground is not impacting the system at the moment since they're each canceling each other out as they lead to ground. But when a fault occurs, let's say on phase A, for example, we see that phase A's fault essentially shorts out the capacitance that exists on phase A. And now we have current flow leading back to the NGR from the fault. And this resistor here is limiting that fault to 5 amps now. And this current is now flowing back to the point of fault and circulating back because current likes to close the loop at the end of the day. This fault current is also taking another path, which is leading up through capacitances of phase B and C, and that's what causes a little bit of an overvoltage on phases B and C, where their potential from B to ground and C to ground gets increased from 277 to 480 volts. Our phase A to ground remains at 0 volts, assuming that this is a bolted fault, so it matches the potential of ground, and our neutral gets elevated to 277 volts so that current can flow through the resistor. Otherwise, if the neutral was at 0 volts here and this ground is at 0 volts, there could be no possibility for current to fall through this resistor in this case. You could see on the top right here that our vector diagram essentially shifts upward where our line-to-line voltage still remains intact at 480 volts. This allows us to have process continuity even for the faulted feeder while not tripping any part of the system and identifying that this first fault is currently present. So NFPA 70E is a standard for electrical safety in the workplace. We also have an equivalent one in Canada, which is CSA Z462. And inside Annex O.2.2, it says that design option decisions should facilitate the ability to eliminate hazards or reduce risk by doing the following. Reducing the likelihood of exposure is one of those points. In this case, out of all the incident energy reduction methods outlined in Annex O.2.3, there are actually 9 of them. High resistance grounding is the only one that is reducing the likelihood before the arc is in the system. So in having that resistor there, we're essentially planning ahead of time and being proactive with respect to the first phase to ground fault that can occur. Now, when we place an NGR there that is 10 amps or less on a system that's 5 kV nominal or below, when a fault occurs, it's leaving insufficient fault energy and thereby helping reduce the arc flash hazard level. The only issue with high resistance grounding is that it cannot reduce the magnitude, because the magnitude, although it reduces the magnitude for phase to ground failures, a phase to phase or a phase to phase to phase failure is going to bypass the neutral grounding resistor at the source. Because if we have 2 points faulted on either phase A and B or phase B and C, we can see that the fault current between those 2 points is just going to circulate between those two, and the neutral grounding resistor may not see that current. So it will not affect arc flash energy for line to line or line to line to line arcs. But it still does an excellent job at reducing the likelihood for 95% of the cases, which is great. So far we've covered that high resistance grounding is able to take majority of the advantages of solidly and ungrounded systems while eliminating majority of the disadvantages that come with those types of systems. And we can see that there's also a method that we can precisely locate a fault, which is better than in a solidly grounded system where you'd have to trip immediately and do some investigation as to where the point of fault occurs from the feeder that ended up tripping. So here, we're going to show a method of locating faults. In this system, we've placed a resistor from the XO point to ground, and you can see that we have a contactor here, which is basically connected to a wire which is shorting out half the resistance. Now, when a fault occurs, let's say on motor 3 phase C, for example, we know that this fault current is going to flow back to this source here and be limited by this neutral grounding resistor. This current will also flow back to the point of fault to close the loop, since current likes to close the loop in this case. Now, with our relaying technology, we're going to be picking up this ground fault scenario, and then the operator can go to our control panel and activate a feature called pulsing, which will open and close this contactor that is shorting out half the resistance. When we short out half the resistance, we're doubling the current of this ground fault that is circulating back to the point of fault. And as a result, a current signature is made in the system where this opening and closing is switching us between two different amperage points. And we can use a Rogowski coil hooked up to a multimeter to track this back and forth movement to the point of fault. So we check motor 1 and we don't see the back and forth movement. We check motor 2, we don't see the back and forth movement. But we check motor 3 closer to the MCC and we see the back and forth movement. Then we go to motor 3's terminals closer to motor 3. We don't see the back and forth movement. So this fault must be coming from the wires that are leading from the MCC to the motor terminals. And phase C is our culprit in this case. Any questions regarding this expert session can be asked right now. And thank you for attending this expert session.
Tony, there are some questions. I can read it for you.
Yep.
So the first question is, what type of grounding do most data centers use?
On the higher end of data centers, most of them will use either solidly grounded or high resistance grounding. We're seeing that with certain high level companies that are building new data centers at the moment, is that on the top line where the incoming power is coming in from the grid connections, they're utilizing high resistance grounding at that point. But when it gets down to the PDU racks where they need that fourth wire or a concentric neutral, they may switch that system to a solidly grounded system because they have single phase loads to satisfy. So on the upper level, they will have on their three-phase three-wire setups high resistance grounding, and then when they need the neutral, they will introduce an isolation transformer and then convert that system to solidly grounded. Now, in that case, they may have to trip right away when the PDU rack is experiencing a fault of any type, but at least their upstream system is not impacted by that fault coming from the solidly grounded system, and then they can still maintain process continuity on their three-phase three-wire setup. In the case of data centers, time is definitely money, especially when it comes to data and making sure that it's readily available. So banks and technology companies that even a minute or an hour of downtime could impact their revenue greatly by millions or even billions of dollars.
Okay, so someone else asked, why does an NGR require two sets of CT sensor?
Two sets of CT sensors may be required because for, let's say, a generator application, you may have an SEL 700G or another generator-based controller from GE, like a multi-lin. And in that case, that generator controller may be doing some overcurrent protection along the neutral or ground fault pickup that may be auxiliary. The second CT has to be utilized particularly for our resistor monitoring. Now, the resistor monitoring is a new code requirement, especially for us in Canada. In the US, this code requirement does not exist yet, so you may only be picking up for ground fault. But having resistor monitoring is a nice to have just because we're able to detect the open circuit scenario and short circuit scenario. The reason why that's important is because the neutral grounding resistor is essentially your only system ground connection. If an open circuit occurs, then your system becomes ungrounded and your entire system's floating. Conversely, if your system gets an NGR short circuit, then your system will behave as a solidly grounded system, and you're no longer limiting that fault current to a very specific value. And you're basically exposing yourself to arc flash potentials since we're no longer limiting that fault current.
So what's the advantage of using a low resistance grounding instead of high resistance grounding? In which scenario do I use it?
So for systems that are 480 volts, 600 volts, the standard is to use high resistance grounding with either a 5 amp or 10 amp NGR. The reason being is that for Canadian customers in table 17, if your system is three-phase three-wire, you're using a continuous rated resistor. And if you're limiting fault current to a 10 amps or less using either a 5 amp or 10 amp resistor, you have the ability to alarm the condition of ground fault without having to trip the system. So a lot of customers are utilizing that at the moment to provide process continuity for systems that are 5 kV and below. As you get to systems that are greater than 5 kV, you would need to consider low resistance grounding where you would coordinate with your fault protection scheme at the feeder level to basically limit the fault current to a more specific value to reduce incident energy levels, and then coordinate with your downstream pickup values for ground fault that are coming off of your either sensitive relays or the G function of the breaker if you're utilizing that still. I know majority of the consultants are now focusing on third-party relays for their feeder protection on systems that are greater than 5 kV. And in that case, we would just have to look at what the ground fault pickup settings are, and size the NGR's let-through current in accordance to that pickup, and trip on first fault.
Okay. And I think this will be the last question. So how does the system work in power systems with a standby generator?
So for standby generators, we would have to look at the single line diagram specifically to see how it interfaces with the normal power. If that standby generator is simply kicking in after the normal power has, let's say, been compromised, through some sort of switching method via Kirky interlock or ATS, then we will basically apply a neutral grounding resistor as well to that standby generator if the normal power also has a neutral grounding resistor. From there, we can coordinate the system based on the position of the Kirky interlock and make sure that the system is still protected in the event of a ground fault scenario, similar to the scenario it was in when they were in normal power. Okay, thank you everybody for your attendance, and it is much
Thank you.
appreciated. I hope you enjoyed the presentation.
Thank you, everyone.